Thank you for coming to my presentation. My name is Masanari Kondo, a PhD student at the Kyoto Institute of Technology. In this presentation, I'd like to describe our paper that was published by the Empirical Software Engineering Journal. The title is The Impact of Feature Reduction Techniques on Defect Prediction Models. First of all, I explain the background of our research. Software quality assurance is an important activity to improve software quality, such as test, code review, and performance evaluation. However, recently the size of the software becomes bigger and bigger, while software quality assurance resources are not enough. Defect prediction is a way to remedy this challenge. What defect prediction does is to inspect software and identify entities that potentially induce a defect in the future. If such entities are detected, software developers could align their software quality assurance effort appropriately. In defect prediction, we identify potential defective entities by using a defect prediction model, such as machine learning techniques. To use such a prediction model, we first need to convert entities. Here, entities would be a file, commit, or class into numerical features vectors, a set of features. Then we apply a defect prediction model to detect the entity is defective or clean. For this purpose, we can use tons of numerical features such as McCabe features, Shike features, or features, or something like these. So we have a question: which features should we use? This is because if we use all features, we would have problems such as the curse of dimensionality. Hence, we need to reduce the number of features. So we study the impact of feature reduction techniques on defect prediction. This is the background of our research. Before explaining our results, we first need to clarify the difference between feature selection techniques and feature reduction techniques in this paper. The feature selection techniques is a technique to reduce number of features by selecting a subset of the original features. The feature reduction technique is a technique to reduce the number of features by combining original features into new features. In this research, we study 8 feature reduction techniques and 2 feature selection techniques. We select the 2 feature selection techniques since prior studies reported that these feature selection techniques perform the best in the feature selection techniques on defect prediction. In addition, we use the original features to measure the performance without any feature reduction or selection techniques. I'll explain the overview of our experimental procedure. First, we extract a set of original features from the target entity. Second, we apply the feature reduction or selection techniques to the set of original features to generate or select a set of new features. Third, we apply supervised or unsupervised defect prediction models to evaluate the feature reduction or selection techniques in terms of the defect prediction performance. Finally, we repeat this procedure 100 times by out-of-sample bootstrap sampling. We evaluate the feature reduction or selection techniques in terms of the performance and variance. Concretely, we use AUC, IQR, and the Scotch-Not EST test. The AUC evaluates the balance between the true positive rate and false positive rate. The IQR evaluates the variance of AUC values. The Scotch-Not EST test evaluates the significant difference and effect size for AUC and IQR. So this slide shows the defect prediction performance for feature reduction and selection techniques as box plot with the Scotch-Not EST test result. Different color indicates a significant difference. The higher value, the better performance. We observe that for the supervised learning defect prediction models, the feature selection techniques, the correlation-based feature selection technique and the consistency-based feature selection technique, significantly outperform the other feature reduction techniques, except for feature agglomeration, FA. For the unsupervised learning defect prediction models, the neural network-based feature reduction techniques, the restricted Boltzmann machine, and the autoencoder significantly outperform the other feature reduction and selection techniques. We also study the variance of the prediction performance across different prediction models. If the variance is small, we could choose any defect prediction models, since any defect prediction models can achieve similar prediction performance. For the supervised learning defect prediction models, we observe that the feature selection and reduction techniques have a significantly smaller variance than the original models. For the unsupervised learning defect prediction models, we observe that the feature selection techniques do not improve the variance, but the feature reduction techniques do. So this is our recommendation. For the supervised learning models, we recommend using the feature selection techniques since the feature selection techniques improve the defect prediction performance and the variance. For the unsupervised learning models, we recommend using the neural network-based feature reduction techniques since the feature reduction techniques improve the defect prediction performance and the variance. So this is a summary. Thank you very much.